is the 25th lecture and we are starting electronics today. We start with a bit of physics which is enough to understand the operation of electronic devices. Should you be interested in more physics, semiconductor physics, you should take one of the electives in physics or the course on physical electronics offered by the electrical engineering department. We shall do only that much that is needed to understand the operation of a diode and a transistor. The first concept that has to be understood or is already known, that conduction of current in any medium, whether it be gas or liquid or solid, conduction of current has to be done by carriers. For conduction of current, you need charge carriers. For example, in gases, it is the positive ions and the electrons which carry current. In liquids, in electrolytes for example, the molecules break up into two parts, positive and negative ions. For example, a dilute sodium chloride solution breaks up into sodium and chlorine. One is positively charged and the other is negatively charged. And under the action of an electric field, which happens if you put two electrodes, an anode and a cathode, then the negative charges are attracted towards the positive electrode and the positive charges are attracted towards the other electrode, and this is how current conduction happens. For current conduction there must be charges, and the charges cannot go from one place to another, they must be carried by a carrier. Charge carriers are important. In solids, depending on the kind of solid, there can be various types of charge carriers, and solids, according to their capability of conducting current, are basically or broadly divided into three classes. The first is an insulator. An insulator has no charge carriers and therefore no conduction of current occurs through an insulator. For example, the dielectric that you put between two plates of a parallel plate capacitor ideally is required to be an insulator. All right, it is not in practice, but that's a different story. An insulator, the conductivity of an insulator, sigma ins, tends to 0. It does not conduct electric current, it tends to 0. For an ideal one, it is exactly equal to 0. On the other end of the spectrum, we have the metals. Metals are very good conductors, that is, sigma metal is very, very large, it tends to infinity, they are almost perfect conductors. Well, and if current has to be conducted very easily in a metal, obviously there must be a very large number of charge carriers, and how this happens we shall look into it. In between insulators and very good conductors, I have used the term metal, I should have used a conductor, a very good conductor, as for example a metal. In between an insulator and a conductor there exists a kind of material called a semiconductor that is not as poor as an insulator but not as good as a conductor or a metal. In other words, the conductivity of a semiconductor lies between that of an insulator and a metal. The semiconductor normally is a poor conductor of electricity, normally is a poor conductor of electricity, and at absolute 0 temperature the semiconductor is an insulator. At absolute 0 of temperature there are no charge carriers and it behaves like an insulator. But at elevated temperatures the semiconductor conducts not as poorly as an insulator, not as good as a conductor, but in between. Now, to understand the theory of semiconductor, let's have a quick look at how a metal conducts electricity. In a metal, as you know, in any solid for that matter, the structure is such, the atoms are closely packed and there is a regular arrangement of the atoms, which goes by the name of a crystal arrangement or arrangement of atoms in a periodic fashion, is also known as a lattice arrangement. All right. Now, in a metal, a typical metal, is this visible on the screen? In a typical metal, the outermost electrons are usually very loosely bound to the nucleus, and therefore a small amount of energy, maybe a rise in temperature, is enough to dislodge some of these outermost shell electrons, and they wander around freely, and therefore in a metal, a two-dimensional representation, these are the atoms, the nuclei, along with their inner shells of electrons rotating around them. And when an electron leaves a particular atom, it becomes positively charged. So this is a positive ion, and there are free electrons, and these electrons are so free that the situation can be compared to a gas, and the electrons, the free electrons, are said to constitute what is known as an electron gas. At absolute zero temperature, however, at absolute zero temperature, these electrons can move so freely that the conductivity tends to infinity, or the resistance to movement of these charge carriers is absolutely zero, and therefore at absolute zero a good conductor shows zero resistance. When the temperature increases, these nuclei or the ions, they gain temperature, they gain energy, and this energy is kinetic energy, proportional to kT. K is the Boltzmann constant and capital T is the absolute temperature, and that also explains that the energy, the kinetic energy is zero at capital T equal to 0. All right. So these atoms or these ions gain kinetic energy due to an elevated temperature, and they vibrate around their neutral positions. They vibrate, and this energy, the kinetic energy, therefore exposes itself or demonstrates itself in the form of vibrational energy. And as they vibrate around their neutral positions, electrons clash with this. Electrons collide with the vibrating ions. As a result, the electron loses energy to the vibrating nucleus. And what happens normally is that these vibrations are random. The vibrations of there is a certain amount of uncertainty in the vibrating pattern of the nuclei, and this uncertainty is reflected in the form of collisions with free electrons. The collisions can be elastic as well as inelastic. However, we shall consider only inelastic collisions, in which the electron, if it had some energy, it loses completely. All right. So the situation is like this. In absence of an electric field, you forget about this part. In absence of an electric field, that is, normally if this is the position of an electron, well, it moves a certain distance before it encounters a vibrating ion. All right. It encounters a vibrating ion here, and it loses its energy. Gets deflected in some other direction. All right. Then after traveling a certain distance, this distance is called the mean free path. That is, before the distance between two collisions, the distance that the electron can move freely in free space, which is not a constant. It is not a constant. It varies, but you can define what is called a mean free path, an average free path. All right. So it travels this distance, then again there occurs an inelastic collision, the electron is diverted, and this motion, this zigzag motion is random, so that there is no net motion in any direction. If you observe a particular electron under the microscope for a long enough time, there is every probability that the electron shall come back to its original position. All right. On the other hand, if you have an electric field, then an electron, let's say this electron in an electric field, it is accelerated by the electric field. The force acting upon the electron is equal to the electric field multiplied by the charge. All right. And you also know that the electron being negatively charged, it moves opposite to the direction of the electric field. But then there is thermal energy, and therefore it does not just move, it cannot move, because the space is not free. There are ions which are vibrating, and therefore it does have to suffer inelastic collisions. Without electric field, the path is shown by this yellow line. With electric field, there is now a bias. There is a small velocity, attributed or contributed by the electric field. Actually, the electric field contributes to an acceleration in the direction opposite to that of the electric field. The electric field is in this direction. The electron, instead of going, if it was free motion, it would go like this, but it follows the blue path. There is a slight tendency to go opposite to the direction of the electric field, so that after some time, after the same number of inelastic collisions, the position of the electron, it does not come back to its original position. It shifts a distance in the direction opposite to that of the electric field. Is that okay? Now, this being a restricted motion, if you observe this for a sufficient interval, then one concludes that what the electric field does is to impart a certain velocity called the drift velocity in the direction opposite to that of the electric field. That is, the electron drifts in the direction opposite to that of the electric field, and what it achieves is a drift velocity u in the direction opposite to that of the electric field. Why doesn't it get an acceleration? It does. In between collisions, it does get accelerated, so it accumulates kinetic energy, but it loses all its energy after an inelastic collision. All right, it loses to the vibrating ion, and this drift velocity in the direction opposite to that of the electric field is obviously proportional to the electric field. U shall be proportional to the electric field, and we show this as minus E because the direction of motion is opposite to that of the electric field. The proportionality constant is denoted by the Greek letter mu, minus mu E, where mu is obviously the drift velocity per unit electric field. Mu is termed as the mobility of the electron. This term is extremely important for semiconductor physics. It is called mobility, and you can easily see that its units shall be meters per second is the unit of U, and the unit of E is volts per meter, and therefore mu should be meter squared divided by volt second. Is that correct? The unit of mobility is meter squared per volt second. This is an extremely important term. It is physically, it is defined as the drift velocity of a charge carrier under the influence of a unit electric field. Unit electric field means 1 volt per meter. All right. Suppose there is in a medium, you consider a cross section. Let's say the electric field is in this direction, E. You consider a cross section 1 meter squared. All right, and you consider a length of U that is equal to the drift velocity. All right, then the electrons are coming out, electrons are moving in this direction, all right, not quite straight, but after a zigzag motion. It is the drift velocity. If you consider only the drift velocity, then you can consider electrons coming out like this, minus C, minus C, minus C, and so on. So if you consider the total number of charge, total charge that crosses a unit area, obviously this is the current density, total charge that crosses the unit area per unit time is the current density J, all right. The current density shall therefore be equal to the total number of charge carriers that cross this unit area in unit time multiplied by the electronic charge, all right. Now how many electrons will cross this unit area? Obviously the number of electrons enclosed within this volume. So if the number of electrons per unit volume is n, then the number of electrons contained in this cylinder is n times u, and the charge is minus E, and therefore this will be the current density. But u is equal to minus mu E, therefore this will be minus and minus will cancel. U is minus mu E, where mu is the mobility. So it shall be n mu E multiplied by E, all right, which I can write as, you see the current, which direction does the current flow? Current flows in the direction of the electric field, because the electron motion is in the opposite direction and it has negative charge, which is equivalent to a positive charge flowing in the direction of the electric field. This quantity n mu E, if I denote this by sigma, then I have the relationship current density is equal to sigma times E, and sigma is called the conductivity. The unit of sigma, if you take the units of n, mu and E, you can see that this will be mho. Yes, what is the unit of sigma? Mho meter, all right. Why not? Let's look at this. It is very important to understand this. N is per meter cubed, so 1 by meter cubed, number per meter cubed. Mu is meter squared divided by volt second, and E is charge, therefore it is in coulombs, all right. Now meter square meter cube becomes meter, coulomb per second becomes current, amperes. So this becomes 1 by m, ampere by volt, this is mho, and therefore the unit is mho per meter, not mho meter, all right, mho per meter. Conductivity, I have written this also wrongly, this should have been mho, mho, mho per meter, all right. So sigma is the conductivity. Now how does this relate to the famous Ohms law? Well, this is another expression for Ohms law. J equal to sigma E, that is the current density, is proportional to the electric field, is another form of Ohms law. And if you are not convinced, let's consider a conductor. Let's consider a conductor of length L, potential difference is V, all right, and the cross section L area is A. Then the current flowing, capital I, shall be equal to current density multiplied by A, and current density is sigma E. But what is E? E is V by L, all right. So this is equal to sigma A by L times V, and if you denote this by capital G, then you get Ohm's law, that the current is proportional to the impressed voltage. The proportionality constant is the conductance, or if you write it the other way around, obviously the resistance capital R is equal to L divided by A 1 by sigma, and you know that 1 by sigma is called the resistivity rho L by A, the famous relationship for resistance of a conductor, all right. So this is simply Ohm's law stated in a slightly different manner. Now let us look at, we were talking of metals, let us look at a typical metal, let us say copper. Just to bring your just to review some of the concepts, let us take copper, of which the atomic weight is 63.6. Okay, what is a gram atom? Atomic weight expressed in grams. All right. So the number of atoms per unit volume of copper per meter cubed shall be equal to the number in 1 gram atom. What is this number? This is the Avogadro number divided by the volume of 1 gram atom. Now this number is 6.022 times 10 to the 23, and the volume is mass divided by density. The mass of 1 gram atom is atomic weight expressed in grams. Therefore this is 63.6, and at 20 degrees C the density of copper dCu is 8.9 gram per cm cubed, centimeter cubed. This is how people still express the density. Well, you have to convert this to a meter cubed, and the relationship is 63.6 divided by the density is 8.9 times, how much shall this be? 10 to the 6 gram per meter cubed, and this number comes out as 8.43 times 10 to the 28. So this is the number of atoms in 1 cubic meter of copper, and suppose every atom gives 1 free electron, then the number of electrons would be equal to 8.43 times 10 to the 28, number of electrons per meter cubed in copper. All right. Then the drift velocity U, which is the current density divided by n times the electronic charge. Current density is NEU, all right, and current density is the current divided by the cross sectional area divided by NE. Suppose in a copper conductor, let us say capital I is 4 ampere and capital A, the cross sectional area, let us say this is 10 to the minus 6 meter squared. Then you can calculate by substituting these values the drift velocity as 4 times 10 to the 6, all right, divided by n, which is 8.43 times 10 to the 28, multiplied by electronic charge 1.6 times 10 to the minus 19 coulombs, all right, and this calculates out to approximately 3 times 10 to the minus 4 meter per second. You see, the drift velocity is an extremely small quantity, 3 times 10 to the minus 4 meters per second. This compares very unfavorably with thermal velocity. That is, if you elevate an electron to a certain temperature capital T, then it gains energy and it moves because of kinetic energy, and the thermal velocity is of the order of 10 to the 5 meters per second at room temperature, that is 300 degree Kelvin. So the drift velocity compares very poorly with the thermal velocity, and the point of this calculation is that if temperature rises, if temperature increases, what happens in a metal? Resistance increases, conductivity decreases. Now why does this happen? It happens when temperature increases, the electrons gain higher thermal velocity, and therefore the time in between two collisions decreases, all right, and the drift velocity then also decreases and therefore the conductivity decreases, therefore the resistance increases. And this is a property of almost all metals, that the temperature, with temperature increase, the resistance increases. On the other hand, in a semiconductor, the opposite happens. That is, as temperature increases, the resistance usually decreases. And to understand this phenomenon, we will have to understand how the charge carriers are affected by temperature and other physical parameters. How the charge carriers are affected, because it is the charge carriers which contribute to the conduction of current. Without charge carriers, we cannot have any current. The semiconductor materials that we shall be mainly concerned with are silicon and germanium, and more of silicon than of germanium. So let us look at the silicon atomic structure. Silicon and germanium both are fourth column elements of the periodic table. The number of the column denotes the number of electrons in the outermost shell. So a silicon atom typically shall be represented by 4 positive charges in the nucleus and a shell shown with 4 electrons like this. This is the silicon or germanium. They are both in the same periodic column, the fourth column of the periodic table. And the arrangement of the silicon atoms, in space is the so-called tetrahedral arrangement. That is, what we have is something like a cube. If you consider a cube, if you consider space to be juxtaposition of cubes like this, well, another cube here, another cube on this side, one cube up, one cube down, and so on. If you consider space to be occupied by cubes like this, then silicon atoms place themselves, one at the center of the cube, 2 at the upper face, opposite corners, that is diagonal positions, and 2 on the lower face, again at opposite corners. Well, the corner corresponding to this is unoccupied, the corner corresponding to this is unoccupied. And these silicon atoms are bound together by a kind of bonding which is called covalent bonding. Covalent, C-O-V-A-L-E-N-T. Is this arrangement clear? If you take a piece of dice and put a dot at the center, 2 dots on the upper face at diagonal positions, 2 dots on the lower face at the other diagonal position, then this describes the arrangement of a silicon atom. And then you have number of them repeated on the right, number of them repeated on the left, number of them repeated on the top and bottom. All right, this makes a bulk silicon. Now, the bonding that exists between silicon atoms is the so-called covalent bonding. There can be many other kinds of bonding, but for our purpose, for silicon and germanium, the bonding is covalent, and it occurs due to the sharing of electrons between atoms. A typical 2-dimensional picture, I can't show in 2 dimensions a 3-dimensional picture, but a typical 2-dimensional representative picture, representation would be like this. If you look at, these are the positive charges, plus 4, and 1, 2, 3, 4. These are the outermost shell electrons. Now, the atoms place themselves in such a manner that 2 neighboring atoms, they share their electrons. That is, this atom shares 1 electron with this. Similarly, it also shares 1 electron with this. So there is these blue lines, which are kinds of hands. It is a kind of a hand shaking, 8 hands of the central atom, which extend in 4 different directions, orthogonal with respect to each other, 2 adjacent directions being orthogonal with respect to each other, and they share these electrons. From the theory of quantum mechanics, it can be shown that this is a very stable structure. This gives silicon and germanium the stability of the atomic structure that it is reputed for. At absolute zero of temperature, there is absolutely no energy anywhere, and the silicon or the germanium atom acts like an insulator. The amount of energy, it can be calculated from quantum mechanics, that the amount of energy required to knock out one of these electrons from silicon is approximately 1.1 electron volt. 1.1 electron volt. You know the unit electron volt? Energy unit? Okay. Whereas if it is germanium, then it is 0.67, approximately taken as 0.7. All right. Now, this energy can be given to an electron in various ways. You can shine light on silicon. Then some of the electrons will get a quantum of energy, h nu, which if it exceeds 1.1 electron volt, then it will say, hell with you, you are binding, goodbye to you. So it goes out. All right. When it goes out, now it becomes a free electron. It has a lot of space to play around. It is not bound to any particular atom. All right. And it leaves the mother atom, the atom from which it has dissociated, what kind of charge? Obviously positively charged. This positive charge is obviously a fixed charge. All right. It is a fixed charge, that is, the mother atom remains positively charged, the infant electron, it goes out. All right. The vacancy that is created, the vacancy that is created is called a hole, H-O-L-E. All right. Let's take a picture, hole, H-O-L-E. Let's take a picture. Here we show this central atom of silicon. An electron has been knocked out of this either by thermal energy or light energy or some other kind of energy. The electron has been excited enough to move from here to some other position, let's say somewhere here. All right. Then if you consider this region, before this electron, this free electron had entered this region, the region was electrically neutral. But now this region is negatively charged. Similarly, this region where there is an absence of an electron means this hand has now been broken. This hand of the covalent bond, there are 8 such hands, 7 of them remain, 1 of the hands has been broken, and therefore this region has become positively charged, and the vacancy that is created is called a hole. All right. Now, it can be shown from quantum mechanics that current conduction will now occur because there are free electrons, but surprisingly current is also conducted by holes, and it happens like this. Suppose in this structure another electron may be knocked out from some other atom, comes in the neighborhood of this positively charged region, then there is no reason why this electron should not feel inclined or obligated to go to this and fill up this vacant position. That means it brings back the broken hand. So it makes this structure stable. Now, if I look at the picture, there was an electron here, and there was a hole here. So this electron has gone to the hole and made it neutral. As a result, if this electron had belonged to another atom, what would have happened? A hole would have been created here. If initially this was a neutral region, a hole would have been created here. So it is as if this hole, which was in this position, it is as if this hole has moved to a new position. And by sophisticated calculations of quantum mechanics, it can be shown that the hole movement is exactly like that of an electron. That is, the hole, which is a vacancy, now behaves as a positive charge with a charge equal to that of the electron and a mass which is different from that of the electron. In other words, in a semiconductor we have to talk of two kinds of mobilities. There are two kinds of charge carriers. There are holes, there are electrons, two kinds of charge carriers, and therefore we shall have to talk about the mobility of holes. Instead of H we write P, P for positive because holes are positively charged, and instead of electrons we write N, that is the negative charges. All right. And therefore the current density, if we take the same equation as we derived in the case of a metal, the current density shall now depend on electrons as well as holes, and therefore current density shall be N times mu N, this is due to the electrons, times the electric field, plus P times, P is the concentration of holes or the number of holes per unit volume, P times mu P, and both shall be multiplied by E. And therefore the conductivity in a semiconductor shall consist of two terms. One is due to the electrons and one is due to the holes. All right. You should appreciate at this point that in an intrinsic or a pure semiconductor, at any temperature the number of electrons and holes should be the same. Isn't that right? Because every time you create a hole you have knocked out one electron. So one negative charge, one positive charge. All right. This is the story in a pure semiconductor. If it is impure, then the situation is quite different, which we shall come to. But you understand that in a pure semiconductor, which is also called intrinsic, and the meaning of the word intrinsic shall be clear a little later, but in an intrinsic semiconductor, N is equal to P is equal to Ni. This I stands for intrinsic. In an intrinsic semiconductor, germanium or silicon, the electron concentration is the same as the hole concentration, and this is usually denoted by Ni. All right. The two elements, before we go into the intrinsic semiconductor, we would like to have a look. Can you see what is? Can you see this on the monitor? These figures clearly? Not clearly. I'll read them out. Just let these numbers ring a bell when these numbers arise in a certain semiconductor situation. Energy gap, we said 1.1 for silicon, 0.67 for germanium. Energy gap is the energy required to gap the valence band and the conduction band. That is to take out an electron from the valence band and move it to the conduction band. All right. The electron mobility and hole mobility, if you look at these two figures, you see that the electron mobility is much higher than the hole mobility. Holes are less mobile than electrons. This is true in silicon as well as germanium, 0.39 and 0.19. The intrinsic carrier density, which we have just defined, Ni, that is if the semiconductor is pure, then you shall have 1.5 times 10 to the 16 electrons per meter cubed in silicon, and 2.4 times 10 to the 19, 3 orders higher in germanium. Even then germanium is not preferred. The reasons shall be clear later. But anyway, what is the number of atoms per unit volume in silicon? Well, we can make a similar calculation as we did in the case of copper. Avogadro number divided by atomic weight divided by density, and that comes of the order of 10 to the 21, which means that for every 10 to the 5 atoms of silicon there is one hole or one electron. So they are very sparsely populated. It's not very dense, it's very sparse population. In copper we assume that there is one electron per unit per atom, which is not the case here. The intrinsic carrier density, this is at room temperature, that is 300 K, is 10 to the 5 less than the intrinsic concentration of atoms. The intrinsic resistivity is 2300, which is a pretty large number. Germanium is much less, only 0.46, and the density is the physical density, that is grams per meter cube, not kg per meter cube. For very funny reasons, this mixture of units, centimeter, gram, kilogram, this continue in semiconductor electronics. I will not change this. I am not authorized to change this, so I will not do that. All right, it's only IEEE or international bodies like that which can change. But this is 2.33 10 to the 6. When you take this figure, you must remember that the unit is grams per meter cube, not kg per meter cube. All right. Okay. Now, if we take silicon, for example, if we take silicon, you can find out that the number of atoms per unit volume per meter cubed is the Avogadro number, that is 6.022 times 10 to the how much 23 divided by the atomic weight, which for silicon is 28.09, divided by density at room temperature, which is 2.33 times 10 to the 6, and this is simply equal to 5 times 10 to the 28. I am sorry, it was not 21, it is 28. And Ni, that is the concentration of electrons in intrinsic semiconductor, intrinsic silicon, is 1.6 times 10 to the 16. So for every 3.3 times 10 to the 12, what is 10 to the 12? Billion? Huh? Billion. All right. For every 3.3 times 10 to the 12 silicon atoms, you have one electron or one hole, which is really indeed very sparsely populated. And if we calculate the sigma, the conductivity, it is n mu n plus p mu p times electronic charge, yes, and n and p are equal, they are equal to Ni in intrinsic silicon, so it would be mu n plus mu p times this. If you substitute the values, 1.6 times 10 to the 16 for this, 1.6 times 10 to the minus 19 mu n and mu p, then it calculates out to only 4.4 times 10 to the minus 4 mho per meter. Is the unit correct? You compared this with copper. What did you calculate? Copper is 5.8 times 10 to the 7 mho per meter. You see how poor the conductor is. Sigma silicon is much less than sigma copper, and therefore at normal room temperature silicon is an extremely poor conductor of electricity. Question now is, why have silicon at all? Why consider silicon at all for electronic devices? There are two reasons. One minor reason is that semiconductors are materials in which the resistance usually goes down with temperature, and therefore whenever you want to make temperature compensation, for temperature compensation you require positive temperature coefficient and negative temperature coefficient. If you have two resistors in which one is a PTC, positive temperature coefficient, the other is NTC, negative temperature coefficient, then you can cancel the temperature dependence. That's one thing. Number two, you can use either of these two resistors as a sensor for temperature, right? If the resistance changes with temperature, and semiconductor materials are very useful in this context. Many of the instrumentation and control situations sense temperature through semiconductors, and in this application they are known as thermistors. That is thermal resistors or heat sensing resistors, thermistors. This, as I said, is a minor reason. Major reason is that as temperature increases, capital T increases, sigma of a semiconductor increases, and this increase is almost exponential. It might cause an avalanche of conductivity, and this is why we have devices like the avalanche diode or the Zener diode. As temperature increases, sigma increases almost exponentially, and more surprising thing is that if you introduce a very small amount of impurity in the semiconductor, and this process technically is known as doping. Doping, that is, you dope a semiconductor, let us say silicon, with some amount of impurity. This impurity has to be a special kind of impurity. It has to be an element from a neighboring column of the periodic table. That is, silicon has 4 outermost shell electrons. You must inject in silicon a very small quantity of either a trivalent or pentavalent impurity. So, the impurity should be of valency either 3 or 5, and you can see what are the possible candidates. Can you see this? This is the 4th column, and silicon is here, germanium is here. There are other candidates, carbon, tin, both of them can act as a semiconductor. Now, the trivalent impurities are boron, aluminum, gallium, indium, whereas pentavalent impurities, candidates are nitrogen, phosphorus, arsenic, and antimony. There are semiconductors which use neither silicon nor germanium. They use a combination of 3rd and 5th group elements. These are called 3-5 semiconductors, and the most exciting semiconductor of today is the gallium arsenide. That is a combination of gallium and arsenic, gallium arsenide. But we are not going into this. We are considering what happens when a pure silicon crystal is doped with a small amount of trivalent or pentavalent impurity. And this picture tells us what happens. Well, what happens is the following. Suppose you have a pentavalent impurity. For example, pentavalent example, phosphorus, let us say, or arsenic. All right. Suppose it is arsenic. Now, arsenic pentavalent means there are 5 positive charges and there are 5 electrons in the outermost shell. So, what it does is, once it enters the bulk of silicon, well, it takes up a position where normally a silicon atom should be. And when it takes up a position, the neighboring silicon atoms don't know that it is arsenic. So, they extend their hands, and 8 such hands are filled up. 1 electron extra is knocked out of this because 8 electrons make a stable configuration. All right. The 9th one, the 5th one that this arsenic atom had extra is knocked out. So, it becomes a free electron. All right. This arrangement, in this arrangement, therefore, the impurity donates electrons, and therefore, this is called a donor impurity, or it creates negative charge. So, it is called N type of impurity, small n for negative charges. On the other hand, if you inject a trivalent atom, if you inject a trivalent impurity like boron, well, boron has only 3 electrons to give. So, it is a beggar. It is a beggar, it accepts another electron. All right. If it takes the position of a silicon, well, one of its hands cannot be satisfied by the neighboring, one of the hands of the neighboring silicon cannot be satisfied by this, and therefore, there is an unfilled bond or a hole. All right. Therefore, it is able to accept an electron knocked out thermally or otherwise from another atom. So, it is called an acceptor atom, or since it creates a positive charge, it is also called a p-type doping, and this is the point we shall start from next time.